Oi, tudo bem? Morning. Morning. Tudo bom? Still have no response from these guys about your visit. I'm going to reinforce
Thank you.
your request. Maybe we have to start. Francisco, podemos começar? Porque se for esperar todo mundo chegar, hein? Vamos, né? Podemos? Okay, good morning. Morning. Thank you very much. Oh, there's a phenomenon going on here. Every day, less and less and less people here. I think I know why. I have seen the pictures from last night, but this is a real phenomenon. I wish I had a micrograph taken every morning, to do some statistics. Anyway, it's my pleasure to introduce one of the very best experts on the mechanical properties of glass ceramics. Professor Serbena, he did his PhD at the famous Oxford University in 1985 on the mechanical properties of intermetallic materials. But then in 2006, he became much wiser. He spent a sabbatical in our lab and started to work with our favorite material, that's inorganic glasses, right? And then he became really interested in inorganic glass and glasses and glass ceramics. And he has published some of the key papers on the correlation of different mechanical properties with microstructure, with some clever design, how you keep the grain size constant and increase the volume fraction, or keep the volume fraction constant and vary the grain size. Some clever strategies to decouple the effect of grain size with volume fraction transformed, because both affect significantly the mechanical properties. So, Francisco, thank you for accepting to come here, and I really look forward to your talk.
Okay. Thank you for the organizers, and Professor Zanotto, for the invitation to come here to the school. I hope you learn something from this lecture as much as I learned from the other wonderful lectures before me. So I am Francisco Serbena. I'm going to talk about mechanical properties of glass ceramics. And a brief overview of this talk will be about these topics here. Let's see how the time goes. I'll try to speak 1 hour and 10, 1 hour and 20. First thing, we just remind us what is a glass ceramic, which was discovered by Stuckey at Corning. It's always good to say that glass ceramics, the first good property that it was observed is superior mechanical property over glass. So when Stuckey got the crystallized glass ceramic and dropped in the floor and didn't break, it realized that the mechanical properties of this glass ceramic was superior to the glass. So this is one of the key properties of glass ceramics. Usually it's better than the glass, mostly. And just to remind us that the glass ceramic is when you have one or more crystallized phases embedded in a morpho matrix. And the important thing is that it's controlled crystallization. And these properties make it suitable for several applications. Before talking about the results we have, we are going to talk about some fundamental properties. So we'll talk about some elastic, plastic properties, theoretical strength of brittle materials, stress concentrations, Griffith's crack theory, and also mechanical strength and fracture toughness. So when we talk about stress is essentially when you apply force over an area you define the stress as the ratio between this force and the area. You will define strain as you apply this force. The material, it undergoes deformation in the direction of the force. So you measure the displacement divided by the initial length, you have the deformation. You may also apply this force parallel to the surface, so you have a shear force, and then you have a shear stress, which is also the division, the ratio of the force by this area. And in this case, you have a normal deformation. Here you have shear deformation. Shear deformation is defined how much the surface or the displaced laterally by the initial length. So the normal deformation, it is related to deformation volume, and shear deformation, it does not, there is no change in volume, but there is change in shape. So we usually associate the shear with shape and volume with normal deformation. We also have another important parameter, which is Poisson's ratio. As the material is stretched along this direction, it contracts laterally. So the ratio between this contraction by the extension gives you the Poisson's ratio. This property is important for glass. I'll show you in a minute. So for small deformations for a glass is isotropic. So you have Hooke's law, where the stress is related to deformation by the elastic modulus. And if you have a shear stress, you have the shear modulus. In isotropic materials, you have an interrelation between these three constants, the Poisson's ratio, the elastic modulus, and the shear modulus. So you don't need to characterize three of them. Characterize two, you know the third. The other thing is the Book modulus, which is the ratio when you apply pressure to a material, is the ratio between this pressure and the relative change in volume. So this is essentially bulk modulus. And look, if you have a material who has a very high bulk modulus, the Poisson's ratio has a limit, which is about a half, which is a liquid, for example. Polymers, they are very compressible, or a liquid, if you get water, the bulk modulus is very high, so you may apply pressure, you don't have change in volume so much. So for an infinite bulk modulus, you have a Poisson's ratio equals to half. This is related to the structure of the glass, so just keep in mind that the more difficult it is for you to compress a structure, the higher the Young modulus. So how to measure these elastic constants? You may have bending, 3-point bending or 4-point bending. You apply strain gauges on the tensile surface, and then when you apply the stress, well, we apply a load, and then you can convert that in stress, and then you can measure the deformation. By Hooke's law, you know the elastic constants. The other way is by resonance frequency. If you get a small piece of sample and then you just make some touching, it will vibrate in some frequencies, natural frequencies, that are a function of the specimen dimensions, but also of the elastic constants. So if you know your specimen dimensions and you put a pulse that produces these acoustic waves and a detector that detects the signal. So you have the signal, you do a Fourier transform, you find the natural frequencies of vibration. From that, if you do flexure or you do torsion, you can have both the shear motion and the longitudinal motion, and then you can calculate the elastic constants from this. Another way is you get your material, you put a piezoelectric transducer, usually quartz, with different cuts in different directions. So you produce a voltage, it produces either a shear wave or a longitudinal wave, and then this wave will travel across the crystal, reflects back and comes back. You'll detect again. So you measure the time, this travel, you know the distance, you know the velocity of these two waves, and then you can calculate the elastic modulus. If you look at how the elastic modulus varies with glasses, you see that it correlates well with the glass transition temperature. So as your glass transition temperature increases, your Young modulus increases. And this depends on the structure of the glass. We can have a look, for example, in how the Poisson's ratio varies with the atomic packing density of the glass. Remember, I told you, the more open is a structure, it's more easy to compress, so expect open structures to have lower Poisson's ratio, more compact structures to have higher Poisson's ratios. Is what you see here. For example, you have silica, which has an open structure, TD1. It has a Poisson ratio of 0.14. And as you increase, you go to, for example, glasses which has a more 2D structure, or other glasses, alpha selenium, which has a 1D structure, you have an increase in the Poisson's ratio. And metallic glasses, which are very compact, have a Poisson's ratio near 0.4. So essentially, the Poisson's ratio is related to the glass structure. If you look for glass ceramics, usually the elastic modulus, because there are some cases where this is not the case, but usually glass ceramics has a higher elastic modulus than the glass. So here is a table taken from a book, and here you have the crystallized phase and the elastic modulus. So the elastic modulus will depend on the glass matrix, but also on the crystallized phases and how much of them you have. These are how the elastic modulus vary in two stoichiometric glass ceramics. This is a work This work is in a 123 glass, biosilicate, where for a constant crystal size, the volume fraction was vary, and the elastic modulus vary linearly, as well as for another, let's say, Drosophila glass ceramic, lithium disilicate, where the elastic modulus increases linearly with the crystalline volume fraction. So another property that we have is hardness. It's important to stress that the hardness is not a material property. So hardness will depend on how you measure it. And hardness is related to, you can define hardness as a resistance to material penetration, and is related, for example, for how good the material is as resistance to scratch, which has, for example, applications on cell phone screens. So, and also, as you indent, you produce localized press deformation, so you can also state that the relate hardness with this localized press deformation. Why this technique is used generally because it has several advantages. For example, it's simple, it's non-destructive, it's cheap, it's fast, sample preparation is minimal, you can probe small areas, so you can have extract properties from films. And under special conditions that I'm not going to talk, you can estimate, for example, yield stress, creep exponents, whatever. So hardness is not a fundamental parameter. So it will depend on how you measure it. And it's important for several mechanisms like abrasion, wear, erosion. The first hardness scale was MOS, which was developed by the mineralogist. And it's very useful because if you are in the field and you see a rock and want you are in doubt which mineral you have, you may scratch this mineral with your fingernail, and if it's scratchable, it's maybe gypsum or talc. If not, maybe other mineral. And the idea of the scale MOS is that you have 10 minerals, and the one that is above is scratch of the other below, but the other which is below cannot scratch the other above. So if you have a coin and you can scratch, you can decide if it's calcite. If you have a knife, you may decide it's a quartz, if it's not scratchable, or apatite, if it is. So the mineralogists, they can make a series of several minerals, and by scratching who is scratch, you can have an scale. That was the first scratch scale. But nowadays, we have several Vickers harness. So most use these Vickers, but if you go, for example, in metallurgy, you use Brinell, for example, which is a cone. And what is the difference between these hardness tests? It's the shape of the indenter. If you have a Vickers harness, you have this pyramid, which has a definite angle between the faces. It's made of diamond, which is the hardest mineral we know. And you make an impression with an under center load. The ratio between the force and the area of impression, which may be calculated from the measurement of diagonals, gives you the hardness of the material. And when you indent in brittle materials, for example, glass, you may produce these cracks. In this case, this morphology is called radial cracks. You can sophisticate a little bit more doing instrumented indentation. Instrumented indentation is that when you apply a load, you also measure the displacement of the indentor with very high accuracy, typically below nanometer. So in this case, if you imagine you have a phone, your matrix, and then you get your finger and press your phone, you see that you have the depletion of the surface. So your finger pushed down, but if you look around immediately, you have a deflection of the surface. The surface goes down. Is what we see here. This is impression, but under load, you have this elastic pushing downwards movement of the surface. So when you unload the load, you have this unloading curve, which from the stiffness or the inclination during initial unloading, which is related to the spring back of the surface, you can extract elastic modulus of your material. So it's a very localized measurement. And also you can go back down, and you can estimate how much is the area, so you can get hardness. You can sophisticate more, putting oscillation load here, in the coils on the force, and then measure the response of the system. So you have dynamic measurement of elastic modulus and hardness as you go into the material. So this is just to show you the indentation, some indentation curves from minerals that are on the scale of the Mohs scale, showing the increasing hardness of each of one. And when you do indentation in glasses, you have essentially two types of deformations. For glasses which have a more open structure, which means lower Poisson's ratio, your material densifies under the indenter. So that's why we say hardness is related to very localized stress. The stress state, very simply putting, is under the indenter you have a compressive stress, hydrostatic, which is more or less is half or 2.5 ratio, 1/3 or 1.5, or, well, let's say one. The pressure here, it would be your hardness, which is the pressure you apply, divided by 2.5. So if you get, for example, silica, which has a hardness of 7 something, the pressure underneath the indenter would be near 3 gigapascals. So you have this densification. And if your structure is more compact, your deformation will be by shear, which means the density won't vary, but you have a shear of the material underneath the indenter. Usually, you have both of them, so you may have partly densification, partially shear deformation. So if again look how the hardness varies across the glass transition, you see that the hardness of the glass increases with the glass transition temperature. And if you look at the pattern, cracking pattern produced by the same load and the same indenter, with a series of glass with increasing Poisson's ratio, you see that materials that densify, they produce these cone cracks, which are are produced by almost Hertz cracks. So if you have a sphere and you press on a flat surface, you get these cone cracks. But as you increase the Poisson's ratio, the deformation, the deformation mechanism stops from being densification and goes to shear. So in the end, you have the radial cracks, and in the end, you see here, this is typical of deformation by shear, which is a metallic glass. So the Poisson's ratio, which is related to the openness of the structure, gives you what's the damage that you produce by contact stress in a material. So there is a very nice papers by Hoxell on this, that you can go deeper in this. Yesterday, Daniel Cassar showed here, machine learning can give us a very nice idea, so this of a prediction of the hardness of a material. So for the glasses, if you look here, how good is the training with the test sample. And here is the contribution of the network for forming elements and also of the modifiers. So here's high in red is the amount of element you have, and here is the bias, positive or negative. So you see here directly, if you increase silicon, you have it will increase hardness. However, if you put phosphorus, it tends to decrease. Okay? So this gives you guidelines on hardness. And I just talked to him. We have also this for Poisson's ratio and for elastic modulus. So we are in a stage now that at least for glasses, at least for the known compositions, you can predict and design glasses with desired mechanical properties. So what about glass ceramics? In glass ceramics, this is the work again on this stoichiometric biosilicate. You see that here again, crystalline volume fraction for a constant crystal size. You see that the hardness of the crystal doesn't change, but in the residual glasses, it increases up to 40% and then decreases. If you look at the hardness of the lithium disilicate, it increases linearly from the hardness of the glass up to the hardness of the complete crystallized lithium disilicate. So it's essentially here a rule of mix. Here, this is the subject of the Rafael's thesis. So what about fracture? Talking about fracture, you may think, how much energy or how much stress do I need to break a sample? So you may think very easily that, well, let's skip here because the calculations is the same. But here it is. If you have, you have two atoms, and the atom is sitting, one atom is the origin, the other is sitting here. You have this force of the curve. So here is your sample resting at 0 force, and then you have a maximum to separate. Okay? So this maximum force is the stress that you need, theoretically, to separate this material. And for small displacement, it obeys the Hooke's law. So if you make approximation for a small deformation, you have this relation. You can, looking for Hooke's law, you have this expression between the maximum stress related to the interatomic distance and also the elastic modulus. You can combine those two, and assuming that the maximum stress position is a fraction of the the distance between atoms, you find that your theoretical stress to break a glass is about the elastic modulus divided by 10. Can be by 2, by 3. So this is the theoretical strength of a material. So If you have, for example, a silica fiber, which has a stress around 100, so you need 10 gigapascals to break it. You find these values in very small samples and pristine in form. However, when you look for what is the real fracture to stress a material, to break a material, this is a very nice work done by Griffith in the beginning of last century. What he did is he took several glass fibers and measured how the strength varies here with the fiber diameter. And he saw that when you decrease the fiber diameter, you increase the strength. And the strength here is much lower than the theoretical strength. It's typically the elastic modulus by 100 or by 1,000. Sorry, 500 or by 1,000. So how much? So why is this so? So imagine if you have a defect, in this case, an elliptical hole, and under a remote stress. So English showed that at the tip of this elastic hole, this elliptical cavity, the stress here at the tip is amplified. It amplifies the remote stress. And the relation is the longer is the defect, and the more acute or the less is the radius here, the higher will be this stress concentration. So if you take typical values for a crack size of about a micron and the atomic radius of a crack at 10 angstroms, you find that this stress to break is about 60. So if you equals this to the theoretical stress, you get that your experimental value in a presence of a defect is much lower than the Young modulus. So it's E over 600, which is a much more realistic value. Griffith sets the basis for the fracture mechanics by calculating what is the energy necessary to break a sample. So if you have a piece of material that has a defect in it, let's say a crack, and once you apply a stress, you deform it, you store mechanical energy. But when you create a crack, essentially the crack relaxes this stress in near vicinity, so this elastic energy of this volume that is released is available for the system. One way of using this energy is to grow the crack. So if you just think that the elastic energy here, which is the square of the stress by 2E, equals the volume, which you just think a cylinder, okay? So is this area PC squared times T, which is the thickness. This is the available mechanical energy. So just look that this mechanical energy depends on the square of the crack length. But to grow a crack, you just need to create surface. So the energy to create this surface is proportional to the product of the surface energy times the area, which is linear with the crack length. So if you sum up those two, you have this plot. So you have a maximum force that if this crack is below, it doesn't have energy to grow. But once past this maximum, the release of strain energy as it grows is enough for the crack advancement. So you have fracture here. So if you do the math here, you see that the stress to break something is 2 times, it depends on the surface energy, the elastic modulus, and the size of the crack. So if the defect is very small, this stress will be high. And if the crack is big, you have a decrease in this stress. Also, this stress is related to Young modulus. So the higher the Young modulus, the higher will be the stress to break a sample. So usually this is one of the mechanisms of increasing fracture toughness, which is having a higher elastic modulus material. So if you get this relation, which was deduced by Griffith, you can rearrange, and then you see 2 gamma is a material property, and here is the variables of stress and the crack length and material and elastic modulus. So we call this term energy release rate. And this is a material property, is the critical critical strain energy release rate. So as you increase your stress, or the crack grows, once G equals GC, you have a fracture. So you have a criteria for a fracture. You may also rearrange this term here, and you put all the materials properties on the right side, and here you have on the left side the stress only and the crack size, and here is a constant that will depend. Here is square root of pi, but here it will be a factor depending on crack size, crack configuration. You see that this term here is given by materials property, and we call it critical stress intensity factor. And this is the stress intensity factor. So when this quantity reaches K1C, you have a fracture. So you see that sometimes people work on G, sometimes people work on K1C. You have three modes essentially of fracture. You have an opening mode, which is called mode 1. You have mode 2, when the force is applied parallel to the crack face, but perpendicular to the crack front. And you have mode 3, which is the shear mode. For example, when you cut a paper with a scissor, you are cutting the paper in mode 3, because one part of the scissor push down and the other pulls up. So it's mode 3. Yeah? Okay, so you have these three modes. Usually we consider only mode 1, which is for opening material, for propagation of the crack. This stress intensity factor is related to how the stress distribution occurs around the crack for the three modes. So you always can describe the stress field. Just the K1, which is related to a parameter related to how much stress you apply and how the crack size and the constant factor. And you always have the singularity, square root of R, and a term related to the how the angular distribution. So you always see that near the crack, the stress goes up. There is a relation between the G and K, which is given by this. And the reason sometimes you work with G, not in K, is because sometimes you have a crack under three modes of loading. So when you have that, you related the K related to each mode of loading with G using this expression. This is important, for example, in some tests when you want to measure adhesion of films, for example. So in sealants for fuel cells, we have done some tests on it. So you get your interconnect, make a glass ceramic paste, put another interconnect on top, and you want to measure how much is the energy adhesion between the glass ceramic and the interconnect. So you have mode 1 and mode 2 loadings, and then we work on G. So if you look at fracture toughness of the glass, they are usually here, around 0.5, 1, perhaps 1.3 for oxycarbides. And usually, this is for glass as well, so you see that it's not much material. Glasses are brittle materials. You don't have high values of toughness. And one way to determine, do you determine fracture toughness? There are several experimental methods. You have ASTM, a standard for that defines three modes. But one of them is you make a crack through your sample. This crack must be sharp, because if not, it won't be valid. And you break under bending. In some cases, you want the propagation of this crack. You may produce this crack by indentations. And you use the so-called bridge method. This bridge method is like this. You get your sample, make some indentations, and put it in this anvil. This anvil has a space here. So when you compress your sample with the pre-crack downwards, and you compress this empty space here makes the surface crack under tension, so it will propagate as you increase the load, but however here, in the upper middle of the sample, you have compressive stress. So the crack will propagate from the initial size, and will arrest in the middle of the sample, more or less. So this is a way of having good pre-cracks. It depends if your sample is small, how good is your alignment of your setup. So there are several experimental conditions that must be met for you to have a very good pre-crack. We in our lab, I have this fixture here, but never try. I always like to produce pre-cracks by a row of indentations. There is also a method which is you get your sample, make a small defect, and put in a ring and press with a sphere. So you can calculate, by the stress, you can calculate the, sorry. This is the stress. We are talking about stress in K1C, but you can calculate K1C here on these methods. You can use the double cantilever method, which essentially is a slab of material with a crack. You can load this under, if you look in the literature, there are 3 modes of loading. One is a wedge. You put a wedge in it, and the good thing is that your strength intensity decreases as the crack increases. So this is a kind of controlling, the growth of the crack is controlled. Because once you put the edge inside, the crack will grow and stop. So K will decrease with the crack size. If you just try to open, applying a force for each side on this configuration, then you have a condition for unstable crack growth. So here, once the crack starts to grow, it fractures the sample. And if you apply a moment here on each side, essentially your crack does not influence the stress intensity. This is good when you have you don't need to measure the crack size. It's difficult. For example, your sample is not transparent or is inside a furnace. So you know the moment, you know your crack dimensions, you know the K you apply. This is double torsion. We have used these techniques for some time in our lab. So essentially, you support your sample in spheres, and you apply a moment here on the crack. And essentially, you can measure K1C, which is independent of crack size. This was our first specimen configuration to measure, because once we started doing K1C measurements in glass ceramics, we didn't know how the sample or the crack propagation would behave. So we found safer to have a technique that would have a clear crack and long crack, and also just do not worry to measure how long is the crack. So you have this compact CT sample as well. This is a configuration, the single edge V-notch beam, that sometimes you have a ceramic or you have a glass or a glass ceramic that you cannot introduce a pre-crack. So if you cannot introduce a pre-crack, one way of doing it is using this configuration. You just make a notch, and then you get a razor blade with diamond paste, and then you make a sharper notch on the tip. As far as the radius of the tip is smaller than the microstructure size of your thing, let's say if you have a grain of 10 microns, the radius of your notch must be equal or smaller than 10 microns. Then it's a valid test. If you do not meet this criteria, the stress concentration will be high enough, and you will measure a higher fracture toughness than what is the real of the microstructure. And there is another technique as well, it is chevron. Chevron is you get a bar, or you get, for example, this configuration here, and your notch is not straight. You see you have this triangle here. This triangle is the material. So once you start loading here, a crack will start to grow from the tip of this triangle and grows. So it's a good way as well to introduce a crack. This is one of the ASTM standards. Well, at least from my point of view, you need to be careful when you use this standard, because you must not have unstable propagation. This method is based on as the crack grows, the stiffness of your sample will reach a maximum and then will decrease. So you have a very stiff apparatus to measure using this method, because if you increase your load and break, it's not valid. And when you have a soft jig, elastic energy will be stored in the jig. So when you are near the maximum, instead of the stress goes down, the crack will use this elastic energy stored in the jig to grow catastrophically. So you need you don't need a pre-crack, that's the advantage, but however you need a very stiff setup to measure it. The other, I put this because we always use indentation methods to measure K1C. However, I have read several articles, and people call the fracture toughness measured by the indentation is not called fracture toughness. I must stress that. You must call indentation fracture toughness, because what you measure, the toughness you measure using indentation, called KC, not K1C, because they are not related. This stands because the facility you have using the indentation method, you just indent a glass, you have a cracking, you just measure the crack length, and from that you can work out your K1C. So there are ANSYS model, which is a very cited paper, that correlates the KC, which, well, for some materials it correlated, but I'll show you later. But the idea of the method is simple. You make indentation with a load P, you measure the crack size, you know the elastic modulus in the hardness, and you calculate K1C. There is another model, Nihara's model, that is also, this method is a little bit different, but also you can estimate KC from this. From my point of view, Nihara's model produces KC values closer to K1C, but it was demonstrated a long time ago by Keane and Brett in a famous paper, is very well cited, that when you do measurements using, for example, standards from NIST, the KC is not equals K1C. So I'm not saying you can, for example, if we have several compositions, several different microstructures, you want to see what is the best K1C, you may use indentation. However, you must be careful not to say that is K1C, which is a material property. So what you should do, you do a screening, see what is composition has the best KC, and then do a proper measurement of K1C on them, or at least in compositions nearby. Because K1C is time-consuming, you need to prepare samples. You have several experimental conditions to meet it. So this is important. And we also show that in lithium disilicate, if you measure KC and K1C, they're different. So there is no point in stating that indentation technique produces fracture toughness. It's related to. In my opinion, we don't understand so well the cracking produced by the indentation, so that's why we do not breach this gap. This is an open thing here to work. So this is a topic that I must talk because it's very important. We have here Professor Ralph Miller, who worked on this, and I think he's more expert than me to talk about. But as I feel obliged to talk about fatigue of glass. Why? Because water affects mechanical properties of glasses. How it affects? It's essentially when a water goes to the crack tip, it is able to break the bonds between the oxygen and the silica, and then you have a 2 SiOH on the crack tip. So the fact that the water can go at the crack tip and break, it makes the crack propagates. So these are a series of experiments of Professor Wiederhorn that show it that if you have a glass and increase the amount of water in the atmosphere, your crack grows even below K1C. So you apply a load, you do your calculations, the maximum stress is such, and then my glass is safe. But once you apply a stress below that, and you look over time, you see that the crack grows due to the action of the water. So if you look at these curves, you see some regions. The first region is on the left, which there is no crack growth. So there is a threshold for, you can read this graph. Here is the speed of the crack, and here is the applied K. So K1C is here. So if you have well below K1C, below this threshold, you can apply load, you are safe. No crack will grow. But however, once it above this threshold, you have a logarithm increase. So you can write as an exponent n. So the higher the n, the more strengthened is your material. The lower the n, the weaker it will be your sample. And in this case, we call region 1, there are mechanisms, corrosion mechanisms at the crack tip. And the reaction rate of these mechanisms that occur at the crack tip dictates how is this slope. Then you go to a flatter region, which is called region 2, which is dominated by, you have a reaction at the crack tip. So how fast the crack can reach the crack tip, or how fast these reaction products can leave the crack, dictates this region 2. And then you have a much faster region 3 here, where the crack grows faster until it breaks here in K1C. So Wiedenhorn has made a lot of interesting papers. I put them here, just look in the 67 or 70s. As you increase, it varies with glass composition. If you increase the alkali, this effect becomes stronger. It also affects by temperature, so you increase the temperature, the crack will grow more easily, more fast. And also in vacuum, if you increase the temperature, you have this defect more pronounced. And also on pH, so if you make your pH more basic, you decrease the strength of a glass. So here is a pH, a silica glass for pH going from acid to basic, okay? So this is a very important point. I mean, I just put a few slides here, just comment to you, but there is a whole field and unknown questions on fatigue of glass. Professor Miller has done very beautiful work with Joachim Dobiner on putting water in the glass structure and see what is the effect of it. So I invite you to read their papers. So residual stresses. This is important for glass ceramics because once you have a crystal phase inside the glass matrix, you produce it above Tg. So Tg, the glass flows, so it's fine. But once you reach Tg, your glass matrix freezes. And then, as you decrease the temperature, the glass matrix contracts, and your crystal as well contracts. So, but if they contract differently, you have to accommodate this difference in volume, the volume of the crystal and the volume of the cavity lived in the glass. So it depends. If your crystal contracts more than the glass, you have tensile stresses in your crystal. But if your crystal contracts less than your glass, so your glass matrix will compress the crystal. So you see, you have two types of residual stresses in your crystal, depending on the difference between the thermal expansion between the glass and the crystal. Very simply, assuming that you have a very low concentration of precipitates and everybody is homogeneous and isotropic, the Celsius modulus tells you how much is this stress inside the precipitate. So the precipitate here is under hydrostatic stress state, can be compression or tension. And it depends on the difference between TG room temperature, the difference between the thermal expansion between the glass and the precipitate, and the elastic constant. Here, so if you have a precipitate with a higher elastic modulus, the stress will be concentrated more on the crystal. So just keep in mind, the higher the elastic modulus of your crystal or of your inclusion, the higher will be the residual thermal stress on it. And the stress state, it's inside the crystal is homogeneous, it's constant, but as you go outside in the glass matrix, it depends. You see, you have a radial component and a tangential component. One decays with a R cubed, and the other is half of this. And also, they change sign. So if your radial component is positive, the tangential is negative, and vice versa. The stress in your crystal, it varies with how many crystals you have, with your crystalline volume fraction. Because if you have more crystals, they start to interact. So this stress state will affect this stress state. So this has been calculated and essentially is linear. So in the crystal, so if you have a glass with just one precipitate, the maximum stress will be in the crystal and the glass matrix will be with no stress. But as you increase the crystalline volume fraction, your stress in the glass in the crystal will decrease, but the stress in the glass will increase. So for glass ceramics with high crystalline volume fraction, your glass matrix islands that you have in your structure will be subject to much higher stress than your crystal structure. You can, I'll rush a bit because I want to talk about a lot of things, but the stress state varies also with the shape of your crystal. If you have a sphere, if you have a disk, or if you have a fiber, or a short fiber, let's say a cylinder, the stress will vary. And also, the stress will be homogeneous only for a sphere. If you have a platelet or a fiber, the residual stress will vary according to the direction of the inside the crystal. So it's not more a simple analysis. I just go here. So this is important to know. You see, the residual stress depends also on the shape of the crystal. The other source that we have of residual stress inside a high crystalline volume fraction is thermal expansion anisotropy. So usually, your crystal inside the glass matrix, your glass is isotropic, but your glass matrix, so your crystal not. So maybe your crystal will have in one direction a thermal expansion greater than your glass matrix, but in the other direction, smaller. So you have this effect of thermal expansion anisotropy. And also, if you have a crystal inside near another crystal, as they have different orientations, once they contract and the volume must be continued, you start to having the effect of these thermal stresses in here. Just to show you what you see in the microstructure, these are some oxide Thorium spheres inside a glass matrix, and here the thermal expansion of the particles is higher than the matrix. See how the crack grows here? It avoids the precipitates and goes along the tensile stress near each precipitate. But now, if you make it compression, so the thermal expansion is lower than the matrix, this will be in compression. You see how the crack goes towards the precipitates? So residual stress affects crack propagation. I'm not going to talk about much this to you, but you have different patterns as you observed in there. You may also have above a critical size. For large particles above a critical size, during cooling, they have enough elastic energy to produce a spontaneous microcracking. So this microcracking can be in the glass matrix, or here in this case, is a high crystalline volume fraction glass ceramic, and the crack was in a glass particle inside the glass matrix. So you can have a spontaneous microcracking for large crystals. And when you have a remote stress, the difference between the elastic constants between the precipitate and the glass matrix, which will amplify the remote stress more than you think. I'm going to skip this. So when you have this kind of microcracking in the microstructure, you can see that it affects the behavior of your glass ceramic. So here is some examples of some ceramics that you see here is for 1 micron particles. When you do a linear thermal expansion, you have almost no hysteresis. But once you increase to 5 or 15, you see how you have hysteresis, and also the thermal expansion is not anymore linear. This is due to microcracking of the microstructure. And if you put a microphone on it, you see that during cooling, when there is this microcracking, you get these acoustic signals produced during cooling, which is here. So just to show you what can happen. There are some ways of measuring residual stress in glass ceramics. One is X-ray diffraction. So essentially you get a powder which is stress-free. You measure in your glass ceramic. So the stress will make the change in lattice constants, and you measure that doing ritual refinement. We have done that, and we verify Celsius model and other models for a series of glass ceramics. Here, we can measure using X-ray that we can see the anisotropy of the residual stress, but we can only see on the crystal. We cannot measure residual stress in the glass using X-ray, only on the crystals. So these are works, all of them. I can leave you afterwards the reference. And this has been shown in several systems. This is beta-cryptite and beta-spodumene on last glass ceramics, that once you have cracking on the microstructure, they relieve the stress, but your microstructure is microcracked. This is a last system. This is a work of Viviani that produced several in the last system with different crystals as the surface, virgilite glass ceramics, and here the ceram, which is the commercial top cooking produced by Schott. And we measure using X-ray diffraction, calculated with theoretical model predictions, and the agreement is very good. We also measure in PTR glass, where you have these sodium fluoride crystals inside a matrix. We measured using X-ray diffraction, and we also see at a high angle 2 peaks, which is we are close, the crystal size is close to spontaneous microcracking. So what we see in the microstructure, we see a stressed peak, which is related to those known microcracked crystals, and another cracked crystals that are stress relieved. This is a work by Zwesinger and people here in Lamav, where they measure residual stress using NMR in the PTR glass. You can also use fluorescence spectroscopy. For example, if you have aluminum, you have chromium, the fluorescence position, peaks position will change with the stress state. So this can be done for measurement. And you can also use Raman spectroscopy. As far as you calibrate your peak displacement, your peak shift with stress, you can use it. This has been done as well. And indentation technique, just to show you quickly here. This is if you have a precipitate here and you do a series of indentations in the glass, you have this. Very close to the precipitate, you see how the 2 arms are different? So these radial cracks are shorter because they are under compression, and these radial cracks are longer because they are under tension. Due to the difference in thermal expansion between the glass and the precipitate. Here is a reference indentation very far from the crystal. So you can work out measuring these crack lengths, the residual stress in the glass. We just done this. So just to show you the microcracking in that microstructure, it affects the mechanical properties. You can calculate the critical radius of this precipitate. And let's talk about a little bit about mechanical strength. You can measure mechanical strength by bending, as I told you before. There is another technique called Brazilian strength testing. You get a disc and you compress it, and you have tensile stresses here. And this is the test that I like most, is ball on 3 balls. You just get a disc, and then you compress your disc by 3 balls on top and 1 ball in the bottom. The advantage of this testing is that you don't have edge effects. For example, if you go to test bar samples, you see that usually the critical defect starts on the edge of your samples. So if your samples are not well polished, or they may have a defect there, the crack will start to propagate from there. So I always comment that mechanical strength, I don't think companies like to know the mechanical strength. But it depends on sample volume, depends on the technique, depends how you prepare your sample. So mechanical test strength is like indentation. It's not a material property. But anyway, it's well used, so we must prepare our samples very well and state how we do. So the boundary ball test, it eliminates this edge effect. So what you see is a small volume in the center of your sample. So usually the strength of glass ceramics, they are higher than the parent glass. And you must be careful. Sometimes people observe this. If you measure your strength against the distance between the particles, what is here is the mean free path, which is, if you have a crystal here, the mean free path is the difference between the walls of these crystals. So it's not a difference between the center, it's a difference in the glass between those 2 particles. Okay? So you may think as the distance between the center of the crystals less its diameter. Okay? So essentially it's a measure of how much glass distance you have in the middle. So if you do the test, you observe that for samples that are the crystals very far apart, the strength is constant. But below a critical distance, the strength starts to go up. How is that so? Well, the explanation is that if you have crystals very far apart, a critical defect produced by handling, by some bubble, whatever, is able to have any critical size. Okay, so usually as the condition for introduction of this effect is the same, the critical crack size will be the same. So that's why you have mechanical strength constant. However, once you have your precipitate closer, once the distance in the glass is less than this critical defect, you are not able anymore to have a critical defect as big as previous, because you are limited by the distance between these crystals. So, in fact, we start increasing our mechanical strength, because usually crystals are harder, so they limit the critical defect. So this is one way, has been observed, and we observed as well, to increase the strength. I mean, you bring crystals together, okay? There is also, this is a study, it's a long time ago, so we always learn from old studies, that if you have here the precipitates, the strength was measured for precipitates with thermal expansion equal to the matrix, higher and lower. What they found is that the higher strength is obtained for equal thermal expansions. Equal. If increase too much or decrease too much, it induces residual stress. They will help to nucleate microcracks during testing or before, and then you have a reduction in stress. Yes, But these dons were always done on composites, not on glass ceramics, you see? So the idea is to have, like, say, let's say ceramic particles or oxide particles, and you change the glass composition. So you change the thermal expansion of the matrix. But never done, well, we observed that in glass ceramics. So once you go to glass ceramics, you see here the strength varying as the growth temperature. And you see that the strength increases as you have lithium disilicate nucleation. So in glass ceramics, it's more complicated. So once you start nucleating some phases, you increase your strength. This is a work by Boron, it's an old one, 75, okay? And once you get microcracking, your strength decreases. This is show the fracture strength decreases once you have extensive microcrack in your structure. So from the point of view of strength, you do not want to microcrack your samples, okay? Just pull it out. So looking for more controllable tests on mechanical strength. If you look again in this 1, 2, 3 sodium, calcium, silica glass ceramic with constant crystal size, you see that the strength increases with volume fraction and then it stays almost constant. If you look for the prediction of the residual stress, so in this case, the stress in the crystals are compressive, so they should decrease the strength. And when you compare the prediction of the, just adding this residual stress and compare with experimental data, you see that in this case, the residual stress does not affect the strength. Okay? However, what happens here? How can you explain the increase in strength with this crystallized volume fraction? Open question. For lithium disilicate as well, we observe that for a small concentration, you have an increase, so you see almost 50%, and then goes almost linear with crystallized volume fraction. So if you do the calculations, you see that the critical size is smaller than the mean free path. So actually, it's the defects produced in the glass matrix that is controlling, in this case, in these conditions of the glass ceramics with 12 microns crystals, is controlling this strength. So my last topic is fracture toughness, and then I will close. Fracture toughness, if you look in the literature, the most cited papers on fracture toughness, the 4 most cited, the first is Serabon. Serabon was observed that once you start to have wollastonite, you have an increase in strength, see here, and you have an increase in K1C. So, and also this wollastonite is in a circular form, so it forms a network of a circular form crystals that are responsible for the increase in toughness and strength, comparing with the other compositions. The second one is IPS impressed glass ceramics. So if you have impress 1, which is leucite, you have a fracture strength of 112 and a fracture toughness 1.3. Once you start making a network of lithium disilicate glass ceramics, which is impress 2, you have a fracture strength of 400 and also a K1C of 3.3. And this was attributed for a tougher phase with this needle-shaped interlocked structure. So you have an increase in strength and in K1C due to a different phase and with a particular microstructure. The other is enstatite. This was reported in this in their work. It's a very high toughness for a glass ceramic, 4.6, and was related to the clean or instantite. So during cooling, you have instantite in this microstructure, and instantite can have some polymorphs, protoinstatite, orthoinstatite, or clean instantite. And if you have clean instantite, you have this lamellar twinning microstructure that gives you this high toughness. The other one is indialite, which is reported in the literature. So if you have indialite, instantite, and charoite, you have this fracture toughness 4.3, which is very high. It's very good. And this is a microstructure of charoite and indialite. And the other one, the last one, is when you have canacite. So when you have these mica platelets inside your microstructure, you may reach K1C up to 5, which is, I think, is the highest you have in glass ceramics, and essentially is mica plates. So the crack goes, when you reach these mica plates, it deviates, it defoliates the precipitate, so you need a higher stress to make it propagate. So this is one mechanism as well to increase toughness. And we have been working in a couple of years into how to understand glass ceramics. So glass is, there has been advancements, but in glass ceramics it's much more difficult because you have crystal shape, crystal size, you have different properties of the crystal, they are anisotropic, you have different volume fractions. So we focus on two model glass ceramics, lithium disilicate and barium disilicate. Lithium disilicate is because it has compressive stresses and it's extensively used in dentistry. And barium disilicate, it has thermal tensile residual stress inside the crystals. So the idea is to have two model systems, one compressed, one tensile, and you can see what is the effect in residual stress and the microstructure on the K1C and strength of these two glass ceramics. So when you look at how can you increase toughness in glass ceramics, you may list all of these items. One is internal residual stress, which there is a model by Taya, which just states this. If your crystal is under tension, your matrix is under compression. So if you have a crack in the matrix, this compressive stress on the matrix will try to close your crack. So to make it grow, you need to apply an extra stress. So you can work out what is the increase in toughness. And what we found, I just jump here, several conclusions, but we found that the thermal residual stress does not affect toughness. This is demonstrated, for example, in this system, where you see that the prediction is opposite what is observed experimentally. This is also seen in lithium disilicate. This has seen also in some work done during Mariana Villas-Boas' thesis, where she changed the chemical composition of the matrix by making it equal or higher than the crystal. So you induce thermal compressive stresses different. And it was shown that it has, so these are some photos of the microstructure. It was a huge work on finding the heat treatments to obtain the desired microstructure. Just to show here, we measured the thermal expansion isotropy of the phases. So you not only have one phase, but you have a thermal expansion on them. So in some directions, compression, the other is tension. And in the end, we observed that there is no effect. So if you see, the change in K1C is negligible. When we look, the other mechanism that you can increase the toughness is by crack deflection. So a crack in a glass goes straight, but once you see a crystal, it tends to deviate. So here is just to show you some optical interferometry of the fracture surface in the LS2. You see that as you increase the the crystallized volume fraction, the fracture surface becomes rougher. So you can do some mathematical treatment here. You can have like angle distributions related to this roughness here. And then here's the mechanism. For example, if you have a crack encountering a precipitate and this end can tilt, or between two precipitates and twist. So these induce different modes of loading, which increase the toughness. So the rougher the surface, the higher the energy to propagate. So it can work out for this, and you see that in lithium disilicate, it increased, but cannot explain the observed increase in glass ceramics. The other mechanism is crack bowing. So once the crack advances and encounters two crystals, these crystals anchor, they stop the crack. So the crack to continue to grow, it must bow between these two crystals. Sometimes it enters a little bit, it penetrates a little bit, and then it goes. So this has been calculated, how much increase can you have. And what observed is that we call these weak obstacles, how much the crack can penetrate the crystals or not. And we end up having that for low crystallized volume fractions, it doesn't explain. There is also crack bridging trapping. So once the crack passes the crystal stays intact behind the crack. So in order to crack to propagate, you must break this precipitate. So it bridges the cracks faces. So you need, again, another increasing stress in order to break it. So you can calculate how much will be this, and you see that the predicted toughness is higher than what we observed experimentally. But all of these models is valid only for low crystallized volume fraction, up to 30%. So how can you explain the toughness increase up to 100? So I propose a very simple model. Essentially, it makes a rule of mixture. In the simplest case, is a rule of mixture between the fracture of the crystals and the fracture of the glass, and in between you have the elastic modulus of the glass, the precipitate, and the glass ceramic. So you end up explaining very well the whole variation. Just to let you know how the crack interacts with this microstructure. So here we just look at here is the crystallized volume fraction, and you see how the crack grows. So you see crack arrest. Here it arrests in a precipitate. There is crack branching. So you see the crack deviates here. Here is the fracture surface. So you see that the crack here, the sign of crack arrest. See how this, how the cracks, the bowing mechanism and trapping happens. As you increase, you see here crack deflection. Here you see crack bridging. So the crystals bridge cracks. So in order to crack to grow, you need to break these bridges. You see crack branching here. You see the main crack, and there is a branch there. If you have a branch, it stores energy there. You see crack closure here. You see a crystal stopping a crack. And as you increase the crystallized volume fraction, you see here the crack tends to grow in the residual glass, which is under tensile stress. And even higher, you see all these mechanisms of crack deflection, bridging, and branching. So we come up with this kind of scheme explaining as to what you see in relation to toughening. And relation to this mechanism, Dr. Viviana Soares did a very nice work on lithium dental glass ceramics, but the main crystallizes metasilicate. Metasilicate has this house of cards structure and big crystals. So when you measure the fracture toughness is about, or the strength is about 400, which is very high, and also the toughness is 3.5, which is very good. And you see a lot of crack twisting. So this microstructure gives you a very good toughness and bending. However, when you go to nano, you don't have an increase in glass ceramics. In the K1C, you only get an increase in strength. So you see how different microstructures play different on strength and K1C. There is another work that was a work that was published, just resumed very much, but on BS2, which has tensile thermal residual stress in the crystals. What you see is that, remember I told you, usually the crystal phase is harder than the glass. Not in this case. In this case, the crystallized phase is softer than the crystal. So you don't see neither a big variation in hardness, at least you see a decrease, neither in elastic modulus. This is a scheme of the microstructure. We thought would be simple, but it's not. I mean, you have, you see how these dendrites grow and becomes more elliptical, more spherical as you increase the precipitate size. We observe that you have a residual glass inside these crystals, so it varies with the size and the precursor powder. When you do strength, you see that for small crystals, it increases a little bit. For large crystals, there is a decrease. And if you look at the microstructure for these larger crystals, it's because they spontaneously microcracked. And when we do fracture toughness, we observe that the fracture toughness increases with crystal size and increases with crystallized volume fraction. And we see here the same mechanisms observed in ALS2 are observed here in BS2. I'm going to skip here, there is some comprehensive here, but we see that the dependence on does not depend, the mechanism that controls strength in this glass ceramic does not depend also on the distance between the precipitates, but how strong are these precipitates to block the critical defect. What you see here is that for crystals that are small, they have higher amount of residual glass, so the critical defect can penetrate them. So that's why we see a low dependence here. But once you have a bigger crystal, it has more crystallized volume fractions, blocks more effectively the critical defect size. And so that's why we see here this phenomenon. So I will just jump to conclusion, just to finish this, and then we open for questions. So this has been observed, what we saw here in other crystals. I will skip this arc of behavior that we observed as well, the effect of residual stress, and just come back here. So the main features that I want to emphasize when looking for toughness is that, at least up to now, when you increase the crystalline volume fraction, you increase fracture toughness. If you have a high toughness, so if you can crystallize a crystal phase with a higher fracture toughness, this will be good. And also, if your spherulite or crystals do not have a residual glass, better yet. Large crystal sizes, they increase fracture toughness. So if you have a small crystal size, you may see a small increase. But once you increase your crystal size, you'll see a higher increase in toughness. However, you may produce microcracking, which will decrease your strength. So you must look for what application you want your glass ceramic. The other thing is that residual stress does not affect toughness, but affect the strength by microcracking. And a crystallized phase with a high toughness and are very important for obtaining glass ceramics. There are here some important topics that I didn't cover, but you can go and deeply more in mechanical properties that are fatigue. I only show you 5 slides, 6 slides here, but it's a huge topic. I mean, glass attack, water attack glass and affects mechanical properties. So it's important to know that. There is also the mechanism of ion exchange, which is very important for example, here, strength. Tempering, that we see, we didn't talk about it. Indentation cracking, scratch resistance, and wear. So with this, I'd like to acknowledge all those people who have worked and are working with. So Elena is here, Dr. Zanotto, Professor Zanotto has always an inspiration for all these works, and all my PhD students and collaborators, and also for the people who funded and supported this research. Thank you. Okay, thank you.
Thank you, Francisco, for this excellent overview that covers maybe 40 years of work in 1.5 hours. Not so easy to follow everything, though, but it gave, an idea to the students on how many problems can be studied and how many problems are still open in this area. The lecture is open for questions. Yes, Masoud.
Thank you very much, Doctor. I'm Masoud Ospuri. I'm from University of Miskolc. I have just one simple question. In the first claim in the conclusion, it was written that by increasing crystallized fraction, increases fracture of toughness will take place. So my question is that why existing the crystallite inside the glassy matrix of glass ceramic material can just increase the toughness? Because I have something in my mind. If we have a crystallite inside the glassy matrix, it can work as defect in the glassy matrix. And the edge and the boundary of the, crystallite and the glassy matrix can initiate the cracks. So why it just increases the stiffness of the glass?
Thank you for your question. But you see, we are talking about strength, which is different than fracture toughness. When you have a material and then you just apply a load and you see which load it breaks, that's mechanical strength. When you have a crack and you measure how much stress or how much energy do you need to grow this crack, that's fracture toughness. So you are right in your thinking. If you have a precipitate inside a glass matrix, it may act as a nucleation for cracks. You are right. But then your load to fracture, which is strength, will be lower. You see? But when you measure fracture toughness, you assume that you already have a crack. And you want to measure what's the energy for this crack to grow. Okay? So it's different. So you are thinking right, but it is related to mechanical strength. So that's why when you increase the size of your crystals, you increase essentially the crystal stores more energy, mechanical energy that is free to nucleate a crack.
But the strength also increases in many situations. You increase the toughness and the strength.
Then
that's his question.
Then is a play, because, for example, for large crystals and low crystalline volume fraction, when you have microcracking, say a decrease in strength, but after some crystalline volume fraction, it increases. Because you have more crystals in the structure, so the crack may nucleate, but if you have a lot of glass, it can go, but if your crystalline volume fraction is high, the crack will start to propagate, but you see other crystals, so it starts to interact, and if you are 40%, for sure you are not breaking only glass surface, but you are producing crystal surface. The crack, there is permeability. The system, the crack grows, you see crystals, so it must break crystals. So the toughness of the crystal begins to contribute also to the toughness. So in the end, the contribution of the crystal toughness is higher than the microcracking.
I guess, you know, these defects, please correct me, but when these crystals are smaller than the pre-existing defects, you know, glasses have surface defects. If you break a normally if you break a glass, it breaks because of the surface defects that are created during use or fabrication or handling. If these internal crystals, if they are smaller than the surface defects, it doesn't matter. They are smaller. When they become larger, for larger crystal size, when they become really larger than the pre-existing defects, then actually the strength decreases, right? Right. But I have another question, but I'll give space for other people in the room. Yeah, here.
Hello, Professor. Oops, sorry. Thank you for the amazing presentation. My name is João Vitor. I'm from AMAV. I'm working with a technique that we use electric current to heat the sample to crystallize it. And I'm curious if we could relax the stresses caused during the crystallization if we concentrate the current through the glass matrix, what's happening with my samples usually. Do you think it's possible to relax the stress during crystallization by having the thermal gradient between the crystal and the glass matrix?
You see, as far as the matrix is rigid and you cool down, if you have a difference in thermal expansion, you have residual stress. Unless maybe sometimes you have, you may have your crystal and then we have an interlayer with, I don't know, we need to think about, but let's say half of in the middle of the thermal expansion of the glass and the crystal, that would not, the jump in the stress wouldn't be too high, but would have a layer that would diffuse a little bit. For example, people, when you have soda lime glass and sometimes you need to put some in a connector, for example, we have in our lab a plasma, well, we have some material there, and people, you have soda lime here and you have silica or borosilicate. So what they do is they make a gradient composition on them. If you just feed them and heat it up, they will break. But then they do a glass composition that varies from soda lime to borosilicate, for example, in some length. So essentially, you decrease the gradient, so you don't have a breakage because it's spatially is distributed. So in your case, I think if you heat it up, it will decrease. But once you cool down, it will increase the thermal stress.
Okay, got it. Thank you.
Once the glass is below TG, or the liquid becomes a glass, then you cannot release it. You have this delta CTE, the difference between thermal expansion coefficient of the crystals and the glass. You have stress. You cannot anneal these stresses. There's no possible annealing of these kind of stresses. The only way is to have exactly the same thermal expansion coefficient. Then you have zero stress. Yes? See, I'm losing my energy. The first day I was running, now I'm slowly walking, but I can run a little bit.
Hi, I am Caner Aslan from Şecam. I want to ask, how is mechanical strength is sensitive to changes in composition in glasses? Let's say we have a base composition, and if I change 1% or 2% some of the compounds, will it change significantly the mechanical strength?
Mechanical strength, you're meaning, yes?
Yes, mechanical strength.
Okay. The problem with mechanical strength is that it's not a material property. So once you change composition, you must only change glass composition. The glass size must be the same, the standard test, the same machine, same operator, everything. Then you can compare. Then comes the question, you see, what is the origin of your failure? What is the critical defect that you have? So that's why mechanical strength is, for example, I would say if your critical defect comes from handling, you put a piece of your glass on a bench, or just maneuvering. I would guess the harder the crystal, the smaller the defect. Because if you think same load, the harder you produce a shorter crack. And also the higher, the crack size, for example, produced by contact is related to Young modulus, hardness, and essentially Young modulus and hardness and toughness. So I would guess the interplay between these three, the variation in glass composition, would give you a defect higher or lower. You could use, for example, Einstein's, just approximation, Einstein's relation that relates this. So you may calculate under the same conditions what would be the critical size. It gives you a smaller critical size, I would say the strength will be higher. But then if you give you bigger, the strength will be lower. But also if you are in a humid environment, for example, you may have more alkali in one composition that will be more suitable for, water. So all these interplays in the middle. Okay, because usually during strength, your crack may grow as well. That is given by the fatigue properties.
So we can
it's a very complex problem for mechanical strength.
So we can say if we increase knit work former, then mechanical strength will increase directly.
Sorry, if
I increase the percentage of knit work former in the composition, we can say mechanical strength will increase. There is not a straightforward relation, as I understand you mean.
Perhaps. Because you see, for example, as I told you, if you increase the former, like silicon or boron, you may decrease maybe boron or silicon. For example, you may decrease your Poisson's ratio. So your deformation will be more under densification. It has been shown, for example, that a glass that densifies produces a very shorter crack than a glass that deforms by shear. So, for example, if your modifier is boron, or in some glass systems, it's not for all, but some of them, if you increase, for example, if you increase the openness of your microstructure, that increases the densification. I think you will be okay in increasing strength, I guess.
Ralph.
Thanks. Ralph Müller, Berlin. I have a kind of chemical question. So far we discussed about physics, right?
Yes.
You might have known about these papers published by Sellerier and co-workers. Yeah. He watched that sodium ions were pushed or pulled to the surface during crack growth. That means it has an impact on the fracture toughness energy. And my first question is, did you came across to this phenomenon in other glasses as well for other than sodium ion, or is it kind of unique exception so far?
Well, I did not work with ion exchange or effect of water on them in glass or glass ceramics. I studied a little bit. I did some experiments on 2-point bending, and yes, there is this depletion of sodium and so on. What we observed, we did some 2-point bending in some soda lime glasses. And we left in a chamber, humid chamber at 80 degrees for some time, and we measured the degradation of these fibers with passing time. And we observed that in some cases, when you always a decrease, and we saw some carbonates and some OH with carbon and sodium. So actually sodium is inside these compositions. I don't remember if it's calcium as well, but you could see after some time some precipitates on the glass surface that was produced by reaction of what is in glass with is in the atmosphere, carbonates, for example, and with OH as well. So how that is responsible to decrease in the strength, I don't know, because it's attached. I don't know if it acts as a stress concentration, or if it decreases is because you have this depletion of sodium. I don't know, but I observed this.
Okay, you don't. I mean, this process of pulling and pushing of the sodium is really rapid. So it is at the surface of the crack, and it has an effect on the fracture toughness. So you don't measure the fracture toughness of your glass. Huh?
Oh.
You measure something else, so, which depends on the crack rate, on the crack growth rate.
Yes.
So if it's slow enough, and it was slow crack growth from the Cellier, so all the sodium can sum up at the surface, and if the crack is very fast, like during K1C measurements, this cannot happen anymore. That was my question. If you came across to this kind of chemical problem in measuring fracture toughness or not, but obviously this is an exception, right? Up to now.
Well, we always do our fracture toughness measurements as fast as we can, like we do 1 millimeter per minute. But we observed, I mean, the crack always grow. So if you start with a pre-crack like 100 microns, it may grow up to 200, 300 microns deep. We observe that. So that's why I say that fatigue is very important. We need to control that. So when you do mechanical testing, always state the temperature and at least the room temperature humidity. It's very important.
Well, thank you. This is a very good discussion, but I think we have to stop now.
Okay.
Thank you very much again, Francisco. And let's move to the coffee break, but it's 10 to 10. The next talk will start at 10. So we have a short coffee break now, please. Se ela não vier, é melhor. Não, você não. O dela não dá para entender. Mas enfim, agora deixa. Aí ela está aí. Hello. 10:07, I think we have to start now. This is some announcement that you have, but Oscar, pode pôr a sua. Não, ele já, a pessoa já leu. It's a pleasure to introduce my colleague, Professor Oscar Paitio. Professor Oscar Paitio, his favorite hobby is to design new equipment, and you are going to see some of his equipment at LAMAV this afternoon, like a new viscometer, a quencher roller. Now that's his main hobby, but he works on bioactive materials. He had the opportunity to work with Professor Larry Hench, who is the inventor of bioglasses. Oscar spent at least a year, I think, in Florida. 1 year and a half in Florida when Professor Larry Hench, who unfortunately passed away 2 or 3 years ago, but he worked closely with Professor Larry Hench. We actually designed Oscar Paitio's thesis, PhD thesis, here in São Carlos in a bar. So bars are very important. You know, we had a meeting late in the afternoon when Professor Hench was here, you know, having a few beers in a bar, and we designed the idea of his thesis in a napkin. I hope you have a picture. You have a picture of that napkin? Oh, too bad. You have to show that napkin. Anyway, so Professor Paitio also invited a student, Giovanna, and a postdoctoral researchers, Claudia and John Vitor, to help him showing some applications of bioactive materials in the end. So I guess this is a surprise to me. I was informed now, but I guess you give some introduction, and Claudia, Giovanna, and John Vitor will give some examples of applications. Testa aí. Alô? Está desligado? Então? Está desligado o microfone. Testa.
Alô, alô. Ok. Para mudar o... Okay. Now I'd like to thank everybody, and mainly Professor Zanotto and Professor Larry Hench was my father's scientific. I have been with him since I 20. Oh, it's 45 years ago. So we have a lot of histories about my thesis and everything. We decided to share some part of my presentation because in the last school, we noticed that the people are only talking about bioactive ceramics. And now I have to spread a little bit with inert ceramics too. Is the last one. João Vitor will talk about a little bit application, and he is working with his thesis in this area. Claudia will be a review about the properties and the applications of biosilicate. It's a glass ceramic developed during I come back from Florida, and it's have a lot of studies, theses, and patents application with these materials. Giovanna it's a kind of bio and inert material combined the both properties, and we can have an idea about all the applications from inert to bioactive materials, right? Oh, sorry. So, first thing about the biomaterials demands a lot of partners, because I am engineer, I'm not physicist, I am not medical, and you need to get this kind of specialist to work with you, like biologist, biomedic, veterinary, physician, and it's not easy to build this kind of the screen. And it's the first thing that you think when you start to work with biogas, biomaterials. I'm going to give you some background about it. Most of you that work with in this area knows everything about that I'm talking about, but there is a lot of people that is not usually with this kind of concepts, right? We have here in São Carlos 2 spin-offs from Lamave, Vitrovita and Vetra. Vetra is still working and nowadays receive from our Brazilian FDA authorization to produce some biomaterials. Why we need to use materials from glass as bioactive? There is a very key property that you can try to thinking about. It's chemically resistance or not. And in this way, to be bioactive, you need to dissolve some part of your material. Must be reacting the human environment. So, if you think about something to build some biomaterial, need it to be soluble, a little bit at least. If not, just the body recognize like a inert material and make some fibrous capsules inside it. So it's very known in the literature about the hydroxyapatite ceramics. I believe it's the first one, the materials to be used on the bioactive materials. But you see in the last slide of the presentation that we must be go on. Hydroxyapatite was the start point, but we have much more efficient materials, much more bioactive, much more easily to process this kind of materials. So, Larry Hicks proposed in the 60th decade that 5 types of dissolution of these materials. Any glass. First one, type 2, what happened? When you soak any type of gas in water solution, the first thing is occur is a selective leaching, for example, sodium or calcium. And if this ion release just stopping this stage, you see like a pure silicon in the water, and the reaction stop. We call inert materials because you form in water solution a protective film rich in silica. In the other side, the opposite to this behavior is the total soluble glass, like you see, for example, sodium silicate, metasilicate glass. If you lose in your table a piece of glass like this, in 15 days you'll be dissolved completely. So there is no protection. The water solution is still attack until dissolve all the materials. In the bio application is resorbable glass because the organism start to attack and it don't stop. And the new bond or new part of your collagen grow with the solution of this glass. It's resorbable. In the middle of the way, inert or materials like soluble, we have a bioactivity because it's combined the two processes, soluble part and enrich, silica rich, come out, but not dissolve all the materials. It's the middle of the way, combine the both opposite material, inert and soluble, right? Oh, so, just to compare that biomaterial in window glass is not so different in composition. Window glass has 74% silica, bioglass 45 and soluble 46, for example. Okay, what the change is when you go to get materials like reactions, you need to decrease the silica content. And you see the calcium increase, the sodium increase in comparison to window glass. Okay? When you go to soluble, you see the sodium is very high concentration if you compare the windows. But the elements is almost the same thing. Maybe the phosphorus there is no in the window glass, but in the bio, about 2 and 6% of weighting is present. So, I can show you some pictures about this, the consequence of this kind of soluble materials. And you see the first one is an inert material that react a little bit, increase the silica on the interface, and the living body build fibrous capsules. There is no interaction, mechanical interaction, the synthetic and your bone. So, if you take out, it doesn't matter for the body. Okay? There is no mechanical strength, nothing. Just a capsule is formed, and the organs knows that you will not be bad for him. So, when you go to the first step that to create this kind of situation, here, first step is rapid ion exchange. The materials given to the solution, mainly sodium and calcium, and only silicon oxide are keeping on the glass structure surface. After that, if you go very high pH, like 90 and upper, even the window glass part of silicon is destroyed, can destroy the link between silica, oxygen, silicon. If the pH is so high, this is happening in window glass, right? So that means all glass can be corrosive. It depends only the environment and what is attacking the surface of these glasses. So, in the biomaterials, even the second stage, shown here, happens pH neutral. That's the key from the precipitate mineral after these chemical reactions. The window glass, no. So what happens with react a bioactive material with your bone? Bones, our tissues, are formed mainly by hydroxyapatite mineral. And here we have our synthetic materials. And in the middle, we see the reaction thickness with two kind of materials formed, double layer. One is silica-rich, and another one that can link your living tissues is hydroxycarbonate apatite. It's not hydroxyapatite, but it's hydroxycarbonate apatite. There is a difference in crystal structure. So you can just summarize the another stage to leave your materials to be linked or make a strong link of your tissues. The third stage is repolymerization of silicon, because the silice in this kind of material is open and can be reconnect, forming a gel structure. So the silica-rich layer on the bioactive materials is gel layer silicon oxide. And this structure is so open that permits that ions like phosphate or calcium sodium that was delivered from the own materials can be precipitate, forming amorphous phosphate calcium rich film, and only will be crystallized when you associate CO2 and OH in the structure and form finally hydroxycarbonate apatite layer. So that means because you have a double kind of surface, hydroxycarbonate apatite in rich silica. Ok. Como é que eu faço para tocar aqui? Peraí. É preciso... Ah, tá aqui, achei. É aqui, é porque tem... É o vídeo aqui, ó. Aqui, tá. Aí. Ok. Here is summarize this 5 stage of creation, a link between the synthetic material you are born. see. Okay, now it's going. Ion exchange, sodium, calcium, the first stage. And now it will be repolymerase and this is formation of silica gel layer and calcium phosphate inside of this gel layer and incorporate CO3 and OH forming hydroxycarbonate apatite. Okay? So there is a well-known diagram proposed by Heinz, where is the most important bioactive glass in function of the amount of silicon, calcium, and sodium. Here is the 45S5, and decrease the bioactive index and until be inert. This is the range, the composition range that we have to work. Here is resorbable, and here is not glass formation. What does it mean bioactive index? It's the time where 50% of interface between the tissue leaf and the synthetic material are linked. It's not 100%, but 15%, right? The most known is 45S5. It has IB like 12. Okay? Just to have an idea, 45S5 is 12, 12 and about 12. Ceravital is another bio, 6.5. AW, apatite volastonite from Kokubo, a Japanese group, 3.2. Hydroxyapatite, Ceravital is from Germany. I don't remember exactly the group that used this kind of material. And alumina is an inert material, 0. Right? If we're looking for the time for reactions happens, we see the reversible, just in implant is very fast. You see the reactions. You see the reactions happens very in few days. After that, you can find the 45S5 in the time, Ceravital, AW, apatite volastonite, hydroxyapatite in alumina. You see here the first thing that is very important in application. Hydroxyapatite need a lot of time to be link your tissues. Is usually when you use hydroxyapatite, wait 120 days to make some solicitation. Okay. It's completely different from 45S5. In 1 week or two, you have conditions to use the material without problems in the body. So, another thing very important that is connected to bioactivity index is when your material is able to bond and just in bone or in soft tissue too. It happens if you have materials called class A that is possible to link to a collagen, soft tissue. It's a good improvement, because if you use it in some place that you don't have bone, like eye or something like that, you have just collagen tissues. And the materials that are able to link this environment is materials with IB more than 8. Oh, no. Eu vou pular isso aqui, peraí. Pronto. Another thing that you're thinking about is elastic modulus. When you try to produce some biomaterials linked to bone mainly, not to soft tissues, but in bone is very important, because if you see here, the trabecular and the cortical bone has very low elastic modulus, and most of synthetic material is very, very high. And you see here, bioglass 45S5 is very similar from cortical bone. What does matter have two materials, different elastic modulus linking? Here it's try to see what happens when you put it together, high modular elastic and low elastic module, and make some load. If you apply a load spread from each material, with low elastic modulus, we have deformation much more than a high level of elastic modulus. When you link the both, the deformation on the your bone, you much more decrease, and your body, you say this interface is not necessary, because they need to be loaded to be healthy and dissolve the interface. This process called stress shielding. Stress shield dissolve the interface. You lose your implant. That's the problem, and arise from the difference in the elastic modulus. So Heinz has developed a material that is very similar from the bone. If you see this picture, all of them is bigger. So bioglass is everything beautiful. High bioactivity, lower module elastic. The thick layer is bigger than the other one. Make link with soft tissue, but he has lower mechanical properties. Okay? That is the reason that people try to crystallize some composition of bioactive materials to get better mechanical properties. Here you have very small pictures to show you some data. Bending strains, Francisco knows, just tell you about bending strains in K1C. It's completely different thing, right? Cerabon, 215, K1C2. It's the highest K1C that we know in literature. The biggest toughness is from apatite wollastonite. hydroxyapatite, K1C is not, I couldn't find any data. And the bioglass has almost the same bending strength, but the K1C is very, very low. What the consequence? This picture is very low, because here we have an implant in monkey, if I remember. You have here the bones, a bioactive materials, and the test was torsion to see where the fracture will happen. You have three possibilities: in the bone, in the interface, or inside the material. And we can see here, you can see the fracture happened in the material. Means the interface has higher resistance than the material. To solve this problem, we try to crystallize. So it's very important to have this kind of thing, because means the mechanical properties, the implant interface is better than your bone. So you have fracture in your bone, you'll be much better than in the other parts of the implant. See, apatite inside the material. The interface is hard, but the material is not have enough mechanical property. Just to a part on a patent that I made in my thesis. This is crystal fraction, flexural strength, most thing interesting. And Francisco give you a small background in the end of his presentation. Is not the total crystallized, has the best mechanical strength. We get with partial crystallized. So we can keep the bioactivity very high, because you have a glass phase that guarantee your ion exchange every stage, and the mechanical properties enough to be applied. And here we summarize some more than 10 years of work. This is biosilicate, is a glass ceramics that I show in the former slides. Has flexural strength, K1C1, modular elastic is not so high. Bioactivity index is very, very high, is comparable 45S5. And the fracture is inside the bone. To finalize this introduction, why to use hydroxyapatite? Why don't you use hydroxyapatite? Because, first of all, it's not easy to synthesize pure hydroxyapatite. In this process, you have a lot of phases that not hydroxyapatite pure. Low mechanical properties, low bioactivity index, because depends of cellular activities. If you place some implant with hydroxyapatite, need the dissolution in extracellular, need of work cells working. The cells excrete acid, a solution acid, try to phagocytose. I don't know. And attack the particles of your implant a little bit, and the attack promotes a delivery in the solution calcium phosphate and reprecipitate as hydroxycarbonate hepatite. Takes a lot of time because the cells must be all the work. It's different from the bioactive normal glass that only the solution make part of the work. That's it. Claudia will talk about now the application of biosilicate and what we have done in Lamav's group, right? Tira.
Okay. E aqui dá para indicar onde aqui?
Esse para frente. Não, o laser é esse. Esse para frente e esse para trás.
Ah, ok.
O grandão é para frente, que é o que mais usa.
Ok, eu acho que eu vou usar. Aqui não tem? Ah, não, aqui não tem. Aham. Good morning, my name is Claudia. I work in the Federal University of São Carlos with the Professor Sanoto since 2015. Today I'm going to speak a little about the application of biosilicate. I'm going to begin to speak about the bioactivity of these biomaterials. Here is the infrared spectrum, spectrum for BioGlass 45S5. This is the spectrum for biosilicate with one crystalline phase, because the biosilicates can form two crystalline phases depending on the heat treatment. And when you do the heat treatment under 600 Celsius degrees, this for only one crystalline phase, that is the combiite. And in the case of seed, this is the spectrum for the biosilicate with two crystalline phases. These phases are the combiite and the apatite phase. You can observe here that when the biomaterial had not reacting with the simulary body fluid, they present certain characteristics band for the silicon, oxygen silicon banding, and silicon and silicon stretching. And you can see that they are present in all the three biocomposites. After this biomaterial in contact with simulary body fluid, they begin to form calcium phosphate amorphous. After a certain time, the band that characterize this layer begin to split into indicating that the crystallization has begun. This is the parameter that is used to indicate the bioactivity of one biomaterial. And in this case of biosilicate 45S5, you can see they need only 6 hours to begin to crystallize the layer. In the case of biosilicates with only one crystalline phases, you can observe that they need 10 hours to begin to crystallize. And for the case of biosilicate with two crystalline phases, they need only 4 hours. This indicates that biosilicate with its highly bioactive biomaterial. This biomaterial presents other properties, such as antimicrobial properties. They not produce cytotoxicity, and they not affect the DNA. And also, they can help in the production of the new blood vessel, which is so much important during the regeneration process, because this permits to transfer the food for the cells and the oxygen. And without this property, it's not possible to have a good healing process. This biomaterial can be used in different applications. One of these is dentin hypersensitivity. This illness is a painful response to a stimulator applied to the opened dentin tubules. As you can see in these images, tubules connect the outer part of the tooth with the inner part of the tooth. And in the inner part of the tooth, you can observe some cells that are odontoblasts, and this odontoblast is surrounded by some nerve fibers. In this part of the tooth, you can observe that gingiva has receded, and this leaves these tubules opened. This produces that when the tubule suffers one thermal, mechanical, osmotic, or chemical changes, the fluid inside the tubules begin to move and transmit one stimulus to the nerve receptor, and this causes the pain. Then, to resolve this problem, you can close the opened dentinal tube using certain biomaterial. This illness is suffered for approximately 1/3 part of the adult population, and biosilicate has been used as a mineralizing agent in clinical and in vitro study to treat this illness. And they found they had very fast and satisfying resulting in the process of occlusion of these dentinal tubules. Here you can observe one ASEAN micrographs of dentin samples immersed in artificial saliva for 1, 12, and 24 hours. And in the first groups, G1, the sample was treated with Sensodyne that presents potassium nitrate. And in the second group, G2, they were treated with Sensikill that permits the precipitation of calcium phosphate. And in the groups 3, it was used a water-free gel containing biosilicate particle, and in group 4, it was used a biosilicate particle mixed with distilled water. The idea here is close the open dentinal tubules, and in the case of biosilicate, they permit the formation of the hydroxycarbonate epithelial layer, and this permits to close these open dentinal tubules. You can see here that among the 4 groups, only the particles of biosilicate particle mixed with distilled water permit to close this opening dentinal tubules after 24 hours in contact with artificial saliva. This permits to observe that biosilicates can be used for treat this illness. After this was done a clinical trial where 142 patients were divided in 4 groups. One was treated with Sensodyne, the other with Sensikill, and the other with biosilicates in gel suspension, and the 4 groups with biosilicate in a solution with distilled water. After the treatment, they found that biosilicate mixed with distilled water diminished the pain in the very times compared with the other groups. Here you can see the graphs for the values from the pain assessment that was evaluated through visual analog scale. And you can see here that in the case of, this is the group for Sensodyne, this is for Sensikill, and this is the group that was treated with biosilicate in water. And this is, this is the group for the biosilicate in gel. And this is the group for the particle dissolved in water. And you can see here that among all groups, biosilicate in water permits a reduction of the pain quickly. In the first moment, the patient feels a pain of 6.7, and after 6 months, the pain has almost disappeared. Then you conclude that these biomaterials are a good biomaterial for treat these kind of problems. Other application that can have this biomaterial is in the middle ears, because when one person suffers one ear infection, this can lead to destruction of the ossicle chains and causing auditory transmission loss. Then biosilicate can be used to treat this type of illness, to reconstruct ossicular chains. For that reason, biosilicate prostheses were implanted in guinea pigs to evaluate material compatibility, toxicity, or toxicity that is related, for example, when one patient has taken some medicine and discount some disorders in the hearing and in the balance. And vestibular toxicity that is related with the problem in the balance, equilibrium, and the orientation. After the treatment, they found that after 1 month and 3 months, no toxicity or vestibular toxicity was found in the animals whose middle ears were exposed to biosilicate. For that reason, they concluded this biomaterial can be used for this kind of treatment, and then realize some clinical trials using these prosthesis. This is for use as a partial prosthesis, and here is to use as a total prosthesis. Then realized surgeries in 29 patients, 14 with partial ossicular replacement prosthesis with biosilicate, 7 with total ossicular replacement prosthesis with biosilicate, and 8 with bond to do partial replacement prosthesis. After the treatment, all groups showed improvements in the air bone gap. There is one measure to determine if the hearing has been improved. Then they conclude autosilicate, that is the name that they give to this prosthesis, is a good treatment for this kind of illness. Other application that we can find for biosilicate is in orbital implants. You can see here that, for example, one patient has acute eye injury, or they present one intraocular tumor, or one person that has one blind eyes, and these eyes present so much pain. It is necessary to extract these eyes. And the physician realized certain surgical procedures such as enucleation and evisceration. These two procedures are similar. In the case of, I think that I should, in the enucleation, the entire eyes, including the globe, is removed by the orbital content, are left in place. You can see here that this blue circle is a part of the eye that the physician will remove. And in the case of evisceration, it's a similar process, but the sclera, the outer layer of the eye ball, will left inside in the orbital. Then when these procedures are realized, the patient will have one void inside the orbital, and this void needs to be filled, because if the patient doesn't receive this treatment, his face can become too deformed. And also these treatments are doing because for aesthetic restoration, for the self-confidence of the patient. Then has been using different materials for this procedure, such as glass in the front of spheres, silicone, polymethyl methacrylate, polyethylene, polyethyl fluoethylene, and alumina. But this material preserves surgical complications such as suture dehiscensis, that is when the physician puts together the tissue, but after the surgery, these tissues can be separated. Also can cause a mechanical trauma, exacerbated inflammation, and implant extrusion that is similar to suture dehiscence. Is this one separation of the tissue, but also it can form translucent membrane over the implant. And low motility. This is so much important because low motility is important for aesthetic purposes. Because when you put one implant, you decide that the movements of the eyes are synchronized. And if the ocular implant doesn't bind to the tissue, they can have one motility that is inadequate, and the movement of the eye can be different. In the case of biosilicate, biosilicate can't bind to the tissue because they form the hydroxycarbonate epithelial layer, and this permits that the movement of the eyes will be synchronized. Other material that has been used for this is porous bioactive hydroxyapatite-based implant. But this material presents certain limitations, such as limited ability to bind to soft tissue and support fibrovascularization. They also present high percentage of extrusion of hydroxyapatite implants, and also has been found small hydroxyapatite particles in the circulatory system. Thus, material that replaces the orbital volume and binds to soft tissue prevents implant movement and ensures adequate motility of an ocular prosthesis is so much important. This is one in vivo test that was realized using implant with bioglass 45S5 and biosilicate. And you can see that the form of this implant is conical. They were implanted in 51 rabbits that have underwent evisceration of the right eye, followed by implantation of scones made for bioglass and biosilicates with one crystalline phase and with two crystalline phases. After the study of 6 months, they found that no animal presented orbital infection, implant migration, no extrusion, and the morphological analysis demonstrated subduct capsules around of the implant, as this subduct capsule is related with the process of inflammation. They concluded bioglass and single-phase biosilicate with one crystalline phase implant induced a lower inflammation and less subduct capsule formation than the two-phase biosilicate. And annual implants could be alternative material to manage the anophthalmic socket, but the best response is being obtained with bioglass 45S5 and single-phase biosilicates cone implant. After this treatment, the clinical trial were realized in 12 patients who have undergone enucleation or evisceration. They were implanted with biosilicate with one crystalline phase orbital implant and was followed for 6 months. And after 6 months, they found that no one of the patients showed surgical complication or signs of inflammation, dehiscence, or extrusion. No change in vital organs was found, and no migration, formation of abscesses, or inflammation around the implant were found. This tells us that this biomaterial really worked for this kind of treatment. Now I'm going to speak about the application in bone regeneration. During my PhD, I worked producing some scaffolds for bone regeneration, and I'm going to talk about this. I prepared scaffolds using the replica techniques. This technique basically, you use one template that is one polyurethane sponge, and this sponge has one morphology similar to the morphology that presents a trabecular bone. You can see here in this image that the bone presents one porous structure, and these pores are opened, and these pores are highly interconnected, and this is so much important because this permits that the cells migrate inside the bone and facilitated the transfer of food and oxygen and the waste that cell excreted. Okay. Now, this sponge is introduced in one biosilicate slurried, squeezed and dried, and then sintered. And here we obtain our scaffold of biosilicate. But this scaffold is so weak because the structure is porous, and this reduces the mechanical properties, and biosilicate has only low mechanical properties. For that reason, we need to do more infiltration. And then follow with infiltration was doing under vacuum. And after then we introduce again in one slurry of biosilicate, and we obtain our bioas 2P scaffold. After this, we continue doing infiltration because our scaffold continue being continue has a low mechanical properties. For the following infiltration, we used one bioglass named F18, and this bioglass, after 4 times of infiltration, permits to increase the mechanical property of this scaffold. Okay, I prepared two scaffolds using one font with 35 ppi, and other with 45 ppi that have the small pore cells. And here you can see the morphology of the surface of this scaffold. This is the scaffold without the infiltration with bioglass. And you can observe that they present one surface that is non-homogeneous, and they present so many defects. And after the 4 infiltration with the bioglass, you can observe that the surface of the scaffold presents one homogeneous surface, and almost all the defects have disappeared. Here you can also observe that one strop of the scaffold, and inside of the strop of the scaffold, there presents a void. These voids are formed during the sintering process because when the foam is burnt, they let one hollow inside the strop which witness the scaffold. For that reason, we realize all the infiltration under vacuum to force that the slurries get inside of these hollows through the pressure. Here you can observe that this is one strut, and here this hollow has been partially filled. And in this image, you can observe one hollow that has been completely filled. And that's good because this helps us to increase the mechanical properties of the scaffold. This part is part to show that after the infiltration, the porosity of the scaffold decreases, and together with the pore size or cell size. And you can see that the biosilicate scaffold obtained with a foam of 35 ppi produce one total porosity of 18.3 and one pore size of 770 micrometers. And in the scale of the scaffold obtained with foam of 45 ppi, we obtain one porosity of 18.2 and one average cell size of 525 micrometers. Here is the compressive strength for the scaffold, and this is a scaffold without infiltration with glasses, with bioglass. You can see that the compressive strength is so low. And after the infiltration with the bioglass, we can observe that the increase of the compressive strength is 50 times. Here we compare the scaffolds obtained with the foam with 35 ppm that give us one per size of 770 micrometers. And you can see that the compressive strength is 1 megapascal. And here is the scaffold we obtained with the foam with 45 ppm. That presents one cell size of 525 micrometers. And you can observe that the compression strength is 3.3 megapascal, what is considerable compared with our first biosilicate scaffold, that is this. You can observe that we get to increase so much the mechanical strength, reducing the pore size of the scaffold and doing the infiltration with bioglass. Here is one comparison, and you can observe that it's a good difference when you do the infiltration with the bioglass under vacuum. And this is our final scaffold. This is our final scaffold that presents all the property necessary to do bone regeneration, and you can see the porosity is 82%. The cell size is 525 micrometers with one compressive strength of 3.3 megapascal. When we compare this scaffold with the commercial scaffold, you can see that we have one parameter similar to those offered for the commercial scaffolds. In the case of Reprobond, they present one total porosity of 18% and one average pore size around 200 and 800 micrometers with one compressive strength of 1.5 megapascal. That is in the case of our scaffold. We present porosity and pore size similar, but our compressive strength is higher. In the case of the other Kronos and Endobond, they can present a higher compressive strength, but they only present a lower total porosity and lower pore sizes that can't increase the mechanical strength. Then our scaffold is a good option for this kind of treatment in bone regeneration. And here you can observe one example on how can be this scaffold applied. When one patient has one tumor or suffer one trauma and some part of the jaw has to be extracted, it is necessary to put one biomaterial that helps in the bone regeneration. The idea here is that is this biomaterial, we have such a template to create one structure similar to the bone of the jaw, and then with the time this scaffold will disappear. And this place is ideal for this biomaterial because they present a lot of mechanical strength that is in the range of the compressive strength of the trabecular bone. And in this part of the body, the jaw doesn't experience a high load, and for that reason, we can use this kind of scaffold in this part of the body. As a conclusion, you can say that biosilicate is a highly bioactive glass ceramic that has different applications such as bone regeneration, orbital implants, middle ear ossicle shame substitution, cervical dentin, hypersensitivity.